Hello, everyone, to another lecture. This one's for Friday, April 17th. We're talking about maps. This is Scott, your instructor and best friend and exam buddy, because you guys got an exam today. Well, kind of you have an exam on Monday, but we're going to talk about it today. All right, so we're talking about maps today. And it turns out that really maps and sets kind of go hand in hand. They used to be one lecture, but I pulled them apart for a couple of reasons. One, to give us some time to absorb the material. It's a little quick if I just had them in one. And then two, just so we can space this out a little bit to have time for the exam, have time for project 5. Okay, so we're going to talk about maps. We're going to get into the exam just a little bit, and then we'll get you on your way. It'll be a short one. So when we talk about a map, and a map is in the STL, there is both a regular map and a multi-map. In the STL library. What we're talking about is a data structure that is a set of ordered pairs. Now, the set here is an important operator, and well, I don't mean operator, an important keyword. When we talk about sets, remember that sets are collections of information. They're not necessarily ordered. This is still an associative container as opposed to a sequential or hierarchical container. And our map is a set of ordered pairs. And so these pairs are going to be connections between some key value or some first value, and then some second piece of data, some other piece of value. The uniqueness here is that the key has to be unique, but the value can be whatever it wants to be. It can be a duplicate. It can be equal to something else. Now, this key must be unique is a feature of a regular map. It's not necessarily the same with a multi-map, which we'll talk about later. So under this assumption that our key has to be unique and our value can be whatever it wants to be, this is where we get our set kind of interaction between our different pieces of data. So let's look at an example really quick. Let's say we have this map where we are mapping names to numbers. So we have Finn being mapped to 1, 2, 3, 4, 5. We've got Ray being mapped to 6, 7, 8, 9, 9. Chewbacca is also mapped to 6, 7, 8, 9, 9. And then Kylo is 8, 6, 7, 5, 3. Now, this is getting into kind of this realm of like, well, Scott, what are you trying to convey? Essentially what I'm trying to do here is kind of like a mailbox system where I want to look up Finn's mailbox. So if I want to look up Finn's mailbox, then I'm going to go into my map and I'm going to see what pair or what value is paired with the key Finn. Right, that's going to get me to 1, 2, 3, 4, 5. So what does this look like in terms of our information? It means that we're going to have a bunch of keys that are potentially associated with similar, but still each one is associated with one single mapped value. Okay, so let's keep going for a sec. The implementation is going to rely a lot on this struct of a pair, and this is defined in utility. This is a library, standard library. If you just implement, or if you just grab the STD or STD pair, you're going to get something that works the exact same as what I'm about to lay out in this implementation. But I just want to show you kind of what's inside of it. So it's going to be a struct. Structs mean that everything is public by default. So in this case, we're going to have a double template, both T1 and T2. This is important because our key and our value don't have to be the same data type. We could have an int be our key and then some custom object be our second type, right? There's all kinds of things we can do here in terms of what we put in for type 1 and type 2. But we're going to have a first and a second. This is essentially the thing on the left, the thing on the right, the thing that comes first, the thing that comes second. We're going to have a pretty basic constructor where we pass in references to those two types. We pass in what we want first to be. We pass in what we want second to be. We're going to have a default constructor that's just going to fill first and second with the default constructors of the types. And then lastly, we'll have some kind of copy constructor where we'll take in a different pair and copy in its information. Now, really quick, this is really important. The fact that this is other T1 and other T2, you might be scratching your head thinking, well, yeah, but hold up, that means you're going to get a type mismatch. So how are you going to deal with that? Well, remember that first might have a constructor that can handle a different type. right? My first, which let's say is a floating point number, could have a constructor that could take in an int. So it's okay that these are mismatched, but that also relies on your types having conversions between the two. So if we were to pass in a string and it's going into a Star Wars character class constructor, right? That's not going to work because we don't necessarily have that defined. But this allows us to convert pairs into other pairs and kind of use implicit typecasting. That's basically it for our pairs. We could also go through, there's probably also a less than operator overload that's going to be comparing the first two objects. It's going to be comparing left hand dot first with right hand dot first. And the reason for that is going to be because our maps are all ordered by the first value, not the second value. The second value kind of tags along. The first value is how and why they are ordered. Okay, so let's look at some methods. If we want to make something, right, we want to make this Star Wars mailbox, we're going to define it as a map, and we have to define both of its types. So in this case, the key type is going to be a string, and then the value type is going to be an int. So I'm going to be mapping strings to ints. We need some kind of insert. This insert is going to allow us to add something to our map. The insert relies on a pair being the thing that you're inserting because it needs to know what the type is. That determines the placement inside the map. But then also you need to include the added thing, right? The added value that goes along with that key. And it's going to return back a pair itself. And this pair is going to be a Boolean and an iterator. So the Boolean is going to tell you, yes, insert was successful, or no, insert was not successful. And the iterator is going to be a reference to that pair that you just inserted. Now remember that we're in a single map right now, which means that if I try to add a thing that has the same key, not a thing that has the same value, but a thing that has the same key as something else, we are going to get a false there, a false insert, because we can't insert duplicates into a singular map. If it's a multi-map, we can, but if it's a singular map, we cannot. There's a nice function in the STL called make pair. This essentially calls the constructor for a pair. It's just a little bit cleaner in terms of our code. It's going to make a pair between Poe and 75311. It will then take that pair and then insert it into our Star Wars mailbox. That's going to be like the usability of this map. All right, so erase. We only need the key for this. And this has to do with how our data is being stored internally. We are only really caring about the key type. So in this case, our strings. We don't actually care about the value type from the perspective of the management of the map. The management of the map is going to rely on the key. The value just kind of gets paired along with it. So when we use this erase, we only need the first key type. So in this case, it's going to be a string. So if I want to erase Kylo, all I have to pass in is the string, not the whole pair, right? I only need that key type. And it's going to return the number of elements deleted. So in a normal set, that will turn 0 or 1. You deleted something or you didn't. But in a multi-set, that's going to give you the ability to know if you deleted more than one key value pair. Okay. So obviously, if we're doing this associative container, we definitely want some find operator. This is going to get us an iterator that is pointing to the pair in question. So this is the same thing where we only need to pass in the key. We don't need to pass in the value. So we can pass in the key that we are looking for. So in this case, Finn. And we're going to get back an iterator that's going to be pointing to the pair that is keyed with Finn. So that will allow us to then access the value as well. A single map has a subscripting operator. This is going to give you array-like functionality, but this is important. That's similar to a set. Our map is not sequential. It is a associative container, which means that we're going to get some kind of weird functionality, different functionality. And what happens here is instead of using an index, we're going to use the key type as our operator. So this allows us to do things like once we've made our mailbox, we can just access the fin value, and that will get us the fin paired data. I should say that the fin key, and that will get us the fin paired value. This turns into just a very nice readable code from the user perspective. You fill up your map, and then you just have to access the things using your key values. You don't have to deal with the other stuff, right? You don't have to deal with, in a set, you kind of had to like recreate the object in order to find if it's there. In this case, all we have to do is just search for that key piece of data to get into our pair. So, right, if we were to do something the opposite side, we can assign into an element. We can use that key value as the indexing into that position as well. So this would overwrite the data that is currently paired with fin. It also turns out that this is going to do something behind the scenes for us automatically. If there is no mapping, so let's say I wanted to insert BB8 and I haven't added BB8 to my mailbox, and I were to use something like this addressing or this subscripting operator, and I were to type in SW_mailbox double quote BB8 double quote brace and then equals and then BB8's mail, what it would do is it would go look for BB8, and if BB8 didn't exist, it would create an entry for BB8 and then add the mail number to that entry. That's pretty usable. That's something that's very different than, let's say, like a vector. If you try to access a memory element of a vector before you've allocated it, you'll get a pointer error, right? You're going to get an error that like you can't access that memory location. But here, our map is actually allowing us to do something pretty intuitive, which is just set your pairs by using the key value as your, I'm going to say index, as your subscripting operator argument to then access or define what the value is paired with it. That's nice. That's useful. Now, it doesn't work quite that way in a multi-set or a multi-map because of how the multi-map has to deal with duplicates. So let's talk about that really quick. A multi-map is essentially going to allow for duplicate keys. You'll be able to have you'll be able to have pairs that have the same value of keys. This is similar to a multi-set where it allowed you to have more than one item in the set. In this case, you're going to have two different entries that are both related to fin, but they will have different values associated with them, which is a little confusing. That means that if you do a find, you're only going to find one of them. You won't find both of them. If you have an iterator that goes to the first one, you then should be able to iterate into the next one. When you do a delete or a remove, right, that's going to tell, or erase, excuse me, that's the right word. When you do an erase, that's going to tell you how many of the pairs you deleted that matched the key value that you're trying to delete. Again, very similar to how sets work, but just with these pairs. All right, so again, this means this functionality means that a multi-map does not support this subscripting operator. There just is no subscripting operator because of this double functionality, where you can have, not double, but this multiple key value functionality. All right, so you might be still asking yourself, Scott, why are we talking about sets and maps so much? It doesn't look like you're giving us that much implementation. It doesn't look like you're giving us assignments on it. Well, it turns out that these are both a base, that's not the right word, space-based concept. A foundational concept to when we talk about hash tables. Hash tables are going to be based on this idea where we can have a connection between a key value and then a stored value, and that the key value and the stored value don't have to be the same type, one, but then two, that we can get into some efficiencies about looking up information. And it turns out that finding an element in a hash table is OC. I'm just going to say that again. Finding an element in a hash table is OC. That's very different than finding an element in anything else. Even in a binary search tree, we're still log n. We're still not OC. We still have to make some operations to find that object. But in a hash table, it's OC, which is awesome. It's fascinating. It's wildly different. But hash tables come at the expense of memory. It turns out that you need to have a lot of memory in order for them to work correctly. We'll talk a lot about this next week. I just want to give you a heads up. Why we're talking about sets and maps is because this leads into our conversation about hash tables and hash indexing. All right, cool. So I think that's going to be good. Again, I want you to have a high-level understanding of sets and maps. I don't necessarily need you to have the finesse of the implementation done. It turns out that maps are also implemented using binary search trees. That's just a kind of average for how the STL approaches it. Again, because you get log n based search times. That's the benefit. All right, cool. Okay, moving forward really quick just into this exam that we're going to do today. I'm going to assign it after our class session, so I'll be assigning it right around 2 o'clock this afternoon. You will have until Tuesday at midnight my time being Pacific Standard Time, to get it done. Same rules as last time. It's open book, open internet, open everything. You have to cite your resources. For the most part, people did a pretty good job about that in exam 2. I'll give you a slight suggestion to try to not rely on your resources too much. A lot of people just copied an answer from a source that was kind of tangent to the question, but not actually the question. And so it's something that I don't mind if you use your resources, but like you should be doing some critical thinking in terms of synthesizing and analyzing the resources you're using. Yeah, it's going to be the same thing. There'll be a portion that is practical. There'll be a portion that's conceptual. It's going to be covering the concepts of trees, heaps, and sets. There will be some questions about sets and maps, but they're not going to be too challenging. They're going to be pretty straightforward. They're not going to go deeper than what we've covered in class or in these lectures. The trees and the heaps, they might get a little technical because you did a learning module that should be due today. That dove into kind of the operation, the underpinnings of those two data types. All right, well, good luck. Please bring any questions you have to the class session today. That will help immensely because that will give you some space to get clarification, to get into the kinds of questions I'm going to ask, that kind of stuff. Okay, I'll talk with you guys later. Bye.